All right, and we're back with our next speaker, Artash Nath, and he'll talk to us about seismic vibrations from outer space to subsurface. Take it away, Artash.
Great, thank you. Hi everyone, good evening. My name's Artash, and I'm a grade 8 student going to grade 9. And today I'm going to be talking to you about one of my latest projects on observations. It's called From Outer Space to Subsurface: Seismic Vibrations, How to Measure Them, and the Impact of the COVID-19 Lockdown. Let's get started. All right, first of all, how are seismic vibrations useful? Well, measuring seismic vibrations has many usefuls. First, it can help us understand more about the geology of a planet, such as the interior structure of the planet, the tectonic movements, or volcanoes. Second, it can tell us about weather patterns on a planet, such as dust storms or waves. It can even tell us about meteor strikes, because when meteors collide with the surface of the Earth, they cause seismic vibrations. And finally, seismic vibrations can tell us about the level of human activity, such as the level of transport or traffic on the roads. So seismic vibrations are definitely very useful. But how can we measure seismic vibrations? For that, we use a seismometer. And how does a seismometer work? Well, it's in fact very simple, and it's completely based off pendulums. Let me show you an example. So as you can see, I have a pendulum here, and the pendulum is attached with a pencil. And let's pretend that I am the Earth. All right, so now when the Earth starts moving, the pendulum will also start moving. And if I have a piece of paper, so when I move, the heavy mass on the pendulum will also slowly start moving. And the pencil will start moving on the paper. And if we start rolling this paper, we'll be able to get the level of seismic vibration over time, just using a pendulum. A seismometer works on 3 of these pendulums: 2 sideways pendulums and 1 vertical pendulum to measure the seismic vibration in all 3 axes. In fact, if we want to get more sensitive seismometers, we use something called an inverted seismometer, where we have like an inverted pendulum, so the pendulum is upside down. This means that it's even more sensitive to seismic vibrations and will move very easily. Now, funnily, astronomy and seismic vibrations share a very unique relationship, because on one hand, we spend millions of dollars trying to create seismometers to measure seismic vibrations to understand planetary geology. But on the other hand, we also spend millions of dollars trying to create instruments to isolate or remove these seismic vibrations from other instruments. So an example of this would be the LIGO. To detect gravitational waves using the LIGO, we need to isolate human-made vibrations. If you would like to know a little bit more about the LIGO experiment, you can just, I've in fact given a talk on it, so you can check that out. And there's something very ironic about it, because you use a pendulum both to measure seismic vibrations, as I described in the earlier slide, but you also use pendulums to isolate seismic vibrations. So this is something pretty funny. And all right, so let's move from the Earth to the Moon. As you know, the Apollo missions, except for Apollo 17, carried seismometers to the Moon. Unfortunately, the Apollo 11 seismometer broke down after a couple of weeks, but fortunately, all the other seismometers lasted until 1977. And this formed a nice kind of network of seismometers on the surface of the Moon. So we could measure seismic vibrations on the surface of the Moon, but what causes moonquakes? Because we know that the Moon doesn't have active tectonic plates on the Earth. So how do vibrations form on the surface of the Moon? Well, it can be caused by 2 things. First of all, by tidal forces. Because the Moon causes tides on the water or the oceans of Earth. And the other way around is also there. except that the moon doesn't have any water for us to make tides on. So instead, the gravitational pull of the Earth makes creases on the surface of the moon, which can cause seismic vibrations. The second way to have moonquakes on the Earth, on the moon, is through global contraction. Because the core of the moon is still slowly cooling down a bit and shrinking, which causes the surface to slowly shrivel up, leading to moonquakes. So this network of seismometers that were placed on the moon detected several events. First of all, they were in fact able to detect one meteor strike on the surface of the moon every single day, which is because the moon obviously does not have an atmosphere. In addition to this, it was able to detect 28 shallow moonquakes, which peaked at a magnitude earthquake of 5. And one thing really amazing about the seismometer network on the moon is that they even measured man-made seismic vibrations. How is this? Well, when the astronauts left the moon, they didn't need the ascent module anymore. So they decided to purposefully crash the ascent module onto the surface of the moon. And since they knew exactly where it was going to land and how much this ascent module weighs, they would be able to actually calibrate the seismometer network to make it more accurate. All right, enough about the moon. Let's talk about Mars, the red planet. The first seismometers that were placed on Mars were in the Viking landers, Viking 1 and Viking 2. Now, they both had seismometers, but unfortunately, Viking 1 seismometer did not activate, but Viking 2 seismometer did. But the problem was that, as you can see in the picture, the seismometer was placed on top of the the lander's bay, which meant it was also prone to vibrations caused by the wind, for example, or by the internal machinery of the rover, instead of being only affected by seismic vibrations. So this meant that it was not very accurate in actually measuring seismic vibrations. Like, for example, in this graph here, the top line you can see in the graph is the wind speed, and the bottom is the seismic vibrations. And you can see a really strong relation between the two. So it was not really able to detect any significant seismic vibrations. All right, let's move a bit closer to the present. In 2018, when NASA landed the Mars InSight on Mars. Mars InSight, in fact, does have a seismometer, but they were much better prepared. In the picture, you can see a white dome, which is the seismometer cover. And under this white dome are 2 seismometers, each of them fully functioning. The first seismometer is the main seismometer, and this is the more sensitive seismometer. But under the white dome, there's also a second seismometer as a kind of redundancy seismometer in case the first one failed, as NASA always has redundancies. And by the way, the white dome on top of the seismometers isolated them from vibrations caused by the wind to make it more sensitive. And I'm gonna show you a small video that's you can hear the sonification of the seismic vibrations for different events that this seismometer measured on the surface of the Mars. So first is the wind. It's very faint, but you can still hear it. All right, the next sound you're gonna hear is from the Mars Quake. And this comes up a little bit louder. Finally, the last one is the sonification of the vibrations caused by the robotic arm on Mars InSight. So, as you heard, these seismic events are, so the earthquake was you were very much able to differentiate the earthquake from other stuff, as, for example, the robotic arm movement. All right, so what causes seismic vibrations or Mars quakes on Mars? Well, it doesn't share a tidal force with the Earth, but as once the Mars had an active core, it's still cooling down, which causes global contraction. which means that the core is still cooling down, which again, just like in the moon, causes shrivels on the moon surface, leading to Mars quakes. The Mars Insight Seismometer was able to detect several Mars seismic events. First, it was able to detect 24 Mars quakes that propagated from deep inside Mars's core. So these are much more deeper formed Mars quakes, and they tend to have a lower frequency measured. It was in addition able to detect 150 smaller surface types Mars quakes, which tend to have a slightly higher frequency. Now, let's compare quakes between Earth, Mars, and Moon. All right, so earthquakes on Earth tend to have a much higher magnitude. For example, an example of an earthquake on Earth could have a magnitude up to 9 or even 8 or 9. But on the other hand, on Moon or Mars, you don't really get quakes that are higher than 4 or 5, which means that quakes on Mars and Moon can be thousands of times less strong than the ones on Earth, as the earthquake magnitude scale is logarithmic. But even though quakes on Mars and Moon are much less high in magnitude, they're also much longer. So as you can see here, in the two graphs for the Mars quake and Moon quake, they last to around 2,000 or 1,500 seconds, which comes up to like 30 or to 45 minutes of an earthquake. Whereas on Earth, you only get quakes that are around 20 to 20 seconds, which is much shorter. This is because that on the Earth, we have the ocean, and the ocean actually dampens these seismic vibrations. In addition, on the Earth, the mantle or the crust of the Earth is mostly connected, which means that the vibrations dampen quickly. But on the Moon or on Mars, there's no water to dampen the seismic vibrations from these quakes. So, and also, the crust is divided into many pieces, which means that the seismic vibration lasts for much longer. All right, so enough about Moon and Mars. Let's go back to Earth, because I wanted to find out a bit more about man-made vibrations. So, all right. So there are a couple different examples of seismic vibrations on the Earth that are human-made. For example, there's the train signals. So if you see a train passing on top of a bridge, then it'll cause a very high amount of vibration, and it'll also be for a pretty long time. But in a cruise ship, on the other hand, it slowly becomes around medium high in seismic vibrations and then slowly phases out. Or in a mining or explosion that happens, it's going to be very short and a very high burst of energy. So now let's talk about earthquakes. Earthquakes are very large seismic events, so they can be measured in several seismic locations, as you can see in the graph below. So these signals can be received by seismic monitor stations and can be processed to find out more about the earthquakes. Now, I wanted to finally do an experiment to see how the seismic vibrations changed during the COVID-19 lockdown in Canada. So I picked 6 cities and downloaded seismic data over time for each of these cities. I processed this data using Python. And in fact, this data comes at 100 lines per second, which is way too much because we don't want to focus on each fluctuation. We want to look at the whole trend of seismic vibrations. So I kept averaging the seismic vibration data until I got a kind of trend you can see on the right. And I calculated this trend for all of the 6 cities. So as an example, in Calgary, you can see a pretty significant decrease in seismic vibrations, around 30%. In Edmonton, slightly less, but it's still there. In Montreal, you can also see a dip in seismic vibrations. It otherwise slightly different. I measured an 8% increase in seismic vibrations during the lockdown. In Yellowknife, there was the most decrease that almost halved the seismic vibrations. And finally, home in Toronto, there was also a decrease. So as you guys saw, there was a decrease in seismic vibrations in almost every single of the cities I measured during the COVID-19 lockdown restriction. All right, so the data that that you can get for seismic vibrations, there's in fact a large network of people with seismometers around the globe, and this data is completely open source, and anyone can get and install a mini seismometer called a Raspberry Shake. And I recently got a Raspberry Shake, and I'm gonna be giving you, in fact, a demo of my Raspberry Shake at work. All right, so here in this moving graph, here I hope you can see it. This is the live Sesame data from a Raspberry Shake in another room. Now, it looks pretty uniform, but now I'm going to ask my sister in the other room to jump near the seismometer. Watch what happens. All right, so at the end of this graph, you can see there's a significant bump when my sister jumped near the seismometer. So it's pretty sensitive, and you can get data in real time from this website for any of the stations. So that's pretty cool. And in case you were interested in my experiment about measuring the lockdown, measuring the seismic vibrations in the lockdown, I've created a tutorial that anyone can do it, and it walks you through all the steps of calculating the change in seismic vibrations during the lockdown for your cities. It's available at my GitHub. My GitHub username is Artash Nath. And if you would like to start learning more about seismic vibrations, feel free to join the Software Underground community, which is a place for scientists that like seismic vibrations, rocks, and computers. Thank you very much for listening, and if you have any questions, I would be more than happy to answer them.
Fabulous, Artash. Thank you so much. Very neat, very interesting. Always a learning experience. All right, so let's go to Blake with questions, if any.
Hi, Artash. I have a question for you, and I think you've kind of answered it or clarified it already. I thought that the Mars InSight lander, the device that's supposed to drill into the ground was part of the system to do seismic work, but I guess it's not. So the seismometers are under that white dome, is that right?
That is right, but I'm glad that you brought that point up, because they are linked in a way, actually. Because when the MOLE instrument, which is an instrument that's going to try to drill down into Mars' surface, is drilling, it's going to cause even more seismic vibration, because obviously if you keep banging the surface of Mars, it's going to cause some seismic vibrations. And obviously those vibrations are going to be picked up by the seismometer. So what the experiment that's going to be going on is that when the MOLE is drilling, they're going to see what changes are observed in the seismometer. So this shows what is the transfer of vibration through the surface of Mars caused by the MOLE. So that's also pretty interesting additional experiment that can be made.
Now the MOLE appears to be stuck. I've been wondering if there's a big rock under the ground and they can't get past it. Do you know if there are plans to maybe move it to a different location or something like that?
In fact, I think they've solved that problem, because Mars InSight also has a robotic arm, and they've been using that robotic arm to in fact help the MOLE or readjust the MOLE to help it dig more efficiently and make it dig using the robotic arm.
Okay. Astro YYZ asks, what accounts for Mars quakes? On Earth, we have plate tectonics and lava and things like that. So can you explain that, please?
Sure. Well, obviously, Mars doesn't have an active core anymore, but its core is right now cooling down because it was once super hot and now it's starting to cool down. And it's not completely cooled down yet. And as it cools down even more, it shrinks. And this shrinkage is kind of like you're shriveling up a raisin, right? So as it kind of shrivels up the surface of Mars, we're observing creases in the Mars surface, which in turn causes Mars quakes.
Okay, thank you. And I have another question for you. Do you have a theory at this stage as to why there's, in most cities, a decrease in seismic activity over the last little while during the COVID lockdown? Do you have any ideas why this might be happening?
Yeah, for sure. Because these seismic monitors are placed near cities. For example, the seismic monitor by IRIS in Toronto is right near Leslie's Spit, which is near the harborfront. And these seismic monitors will obviously be recording some of the man-made vibrations. And during the COVID-19 lockdown restrictions, people started to go out much less, right? Only maybe a couple of times a week, and only for essential reasons, because most of us are staying at home and trying to social distance. So obviously the traffic in the streets will be considerably less. So we will observe a decrease in seismic vibrations. And in fact, this also goes to show how of an indicator these seismic vibrations can be on the traffic, the human traffic in cities.
Okay, thanks a lot. That's it for our questions.
Thank you.
Oh, wait. I got one more, I think. Yeah. Yes. Paul asks, he has a vibration app on his phone. Does the Raspberry Pi work in the same sort of way?
Good question. Well, the seismic kind of vibration monitor inside your phone would most likely work through an accelerometer. So when you vibrate, the accelerometer is moving up and down. So you can kind of measure the seismic vibrations that way. But the Raspberry Pi Shake is a little bit slightly kind of a bigger instrument. So it has two parts, a Raspberry Pi and a seismic monitor sensor. So this is a bit different. So inside this kind of seismic module, there is a kind of tube. And as I talked about pendulums earlier inside my presentation, it works on a similar mechanism as that. So a more kind of physical mechanism. Like if you have a spring inside it and a weight, when you shake it, it's moving up and down, which can then be measured. So it's more of a physical method compared to the phone.
All right, very good. One last question. Do you want to be an astronaut?
I would definitely like to pursue a career related to space exploration and artificial intelligence. I'm not completely sure of what I would like to do, but I would definitely want to follow in those topics.
All right. Awesome. Thanks a lot.
Thanks.
All right. Thanks again, Artash. Great presentation.